People who have played tabletop role-playing games such as Dungeons and Dragons or Imitations have probably had the fortune or misfortune to deal with random encounters in the past. People also use various things, such as various repellents or attractants, consumables in these games, to either increase or decrease the chance of having random encounters. Well, we also say increase or decrease the probability of random encounters. So probability is the likelihood of an outcome or a group of outcomes. So if we have, say, a spinner, which is a disk that is subdivided into sections, like a pie, so radial sections, each an arc from the center, or a fan shape, we can say. Well, this might be complicated if you think of a spinner that, say, has sections that are like this. So the sections actually overlap. Wait a second, guys. Guys, this is just a section of its own. So instead of, red or green, which would be both of them put together, we have red and green, or only red or only green. So for a group of outcomes, there are and statements, or statements, and so on. But an outcome is the one we're going to be dealing with for now, because as this section title suggests, this is for simple probabilities. So an outcome is a possible result of an experiment. When you do an experiment, you will always get something. You will always get an outcome. The chance of some outcome occurring is 1. 1 is certainty. 100%? 100%? Well, hey guys, this here is just out of 100. Per cent. Cent is for 100 as per century or centurion, or, well, cent in terms of money. So if you roll a 6-sided die 100 times and they all come up 6s, well, first of all, you always got a result. Good. You haven't done something wrong when you're doing the records. But you would be very rightly suspicious that this 6-sided die is actually fair, unless you look at all the sides and all of them are written 6. In which case, yeah, it's a fair die. Probably. Or at least you would think so. But we'll get to that, like, intuition a little bit later. The experimental probability is a probability you find by running experimental trials. The more trials you run, the closer your experimental probability will be to the theoretical. Because, well, hey guys, I flipped this coin that has 2 faces once, and I conclude that it must always come up heads. What are you doing? No. One outcome from one trial tells you absolutely nothing. You need many trials to actually get an experimental probability that can actually be worth using. Sometimes the experimental probability is called the statistical probability or empirical probability, because statistics are from a sample, parameters are for a population, so the entire group that could be sampled from. You get parameters, such as, the average height of everybody in a country. Sir, if you're actually trying to figure out the average height, you are probably not going to actually go out and measure everybody in the country. Unless this is a really small country. So, what do we do instead? We do a sample, we collect some people, and then we measure their heights. So we get a statistic. Empirical, well, empiricism is a principle that you must experiment to actually to be sure of anything, or be reasonably sure that it's not wrong. because in science you can't really be sure of anything. So the empirical probability, well, that's number of times that your desired outcome happened divided by the total number of trials. And this is a probability of that outcome. It could be outcome A, or it could be outcome B, in which case it's number of times B happened divided by the total. You don't necessarily put a T here. This NT can also be written just as N. And later on in statistics, it generally is written just as N. But for now, we write it like this because a lot of textbooks at this level do have it as NT. So let's suppose we spin a mystery spinner. A spinner has a little rivet in the middle, perhaps with a hole in the center. And this rivet affixes a little pointer to the center of the circle, and you flick the pointer and it spins and eventually it stops. So you spin this spinner once and you get red. What was the experimental probability of getting red on this experiment? Well, the probability of red is equal to number of times you got red over number of times total. Or just N, as I said before. So, this would be 1 out of 1, and this is equal to 1. What's another way of writing 1 in probability? This is 100%. What's 0.9? 90%. What's 0? Well, 0%. 0 is impossibility and 1 is certainty. Now, what might the spinner look like in this case? How sure can we be that this is what the spinner looks like? Well, it could be that the spinner is just all red. Red. We cannot be sure at all because the sample size is just too small. There are not enough trials. Too few trials. This would be like declaring after flipping a coin once and it landing heads that both sides of the coin must be heads. I'm sorry, but for most coins, when you flip them over, you will notice that they are not, in fact, both heads. Okay. We, of course, exclude the coins that actually do have heads on both sides from this argument. Now, let's say we spin the spinner 100 times and we get red 50 times, blue 30 times, and green 20 times. What are the experimental probabilities? We would get probability of red is equal to n red over n. This would be 0.5 or 0.50 for significant digits purposes. You may have dealt with significant digits in, say, physics class or chemistry class before. So, what's another way we could write this formula? Well, that's P blue is equal to N blue over N T. So this is another way. And that would be 30 times out of 100, or equals 0.30. And if you encounter a situation where you do not have enough space for a particular problem, it's generally customary, at least in my track record, that we put a dashed line and then we start a new column, which is P green. Of course, if you end up running out of space again, then you put next C back of page or something. and put an arrow, assuming the backup page is empty, so blank. Or you can say see backup exam or something. So P green is equal to N green. And this is over, well, another way of writing this, N total. So we have shown all three ways you can write the denominator here for the total number of trials. As you progress, you will generally end up with this version later on. So this would be 20 over 100 or 0.20. These are the experimental probabilities. Now, depending on teacher, it may be customary to rewrite. So this is a matter of what were you actually writing? I don't want to have to look up like 5 rows. And also, make sure that you didn't make any adjustments to this side compared to the last time you wrote it out. Because if you moved anything over, well, you need to rewrite this side. So, P blue and probability of green. Now what might this spinner look like? Well, we have 0.5 for red, 0.3 for blue, and 0.2 for green. So we're dealing with half of it is red, and it looks like 30% is blue and 20% is green. So something that looks like this. Now, can we be sure about this? Well, it's 100 trials, so we can be reasonably sure the spinner probably looks something like this, instead of, say, having the red be a tiny slice up here and the rest is all blue and another tiny slice of green. So we can be reasonably sure, think the spinner somewhat resembles this due to sample size. Now, if you've ever read any scientific papers, you often see n equals something. Yeah, n equals 100 in this case, because there were 100 trials, and that's another reason why later textbooks you will generally see them just having n down here when you need the total number of trials. Okay. Because we know that there is always an outcome, the chance of having an outcome is 1, so certainty. Okay, what about adding these outcomes together? Well, what happens when you have 100 people and you say that 0.6 is the probability of someone wearing red and 0.7 is the probability of someone wearing green, and there's one person who doesn't wear either color? Wait a second. 0.6 plus 0.7 is greater than 1. That's 1.3. We could wear, say, mismatched socks if we really wanted to be pedantic about it, or better yet, red hat, green shirt, or red shirt, green pants, or whatever combination. They may or may not clash horribly. The probabilities we are actually adding together must be individual outcomes that do not overlap. So they are mutually exclusive. So we would end up with wearing red but not green, wearing green but not red, wearing both red and green, and wearing neither red nor green. So these would not overlap, and these probabilities would have to add up to 1. Because, well, this person is going to have to fall into one of these categories. There has to be an outcome on the verdict of how are they in terms of wearing red and or green. If they're wearing nothing, well, that's neither red nor green. We often, in addition to using probability for math, also use probability in everyday settings. Like, for example, if you have 322 lunchtime rush hour customers per day for a sandwich store, well, say 165, so slightly more than half, bought pork, and 87, slightly more than a quarter, bought beef, and the rest bought veggie sandwiches. Well, you should make about 2 pork sandwiches for every 1 beef and 1 veggie, although you might want to gather more data over time, or just look at your stock of leftover sandwiches from the previous day. Yeah, it's quite likely that over time you'll adjust your ratio to be better suited to your average customer levels, tastes, whatever, depending on, of course, what field you work in. So that's a matter of probability. It's a matter of considering your data and considering the ratios you need to deal with it. And then we have people just eyeballing things, like say, oh, I'm 99% sure that I just did well on that test. Or, I think there's a 20% chance it'll rain today. Now, yes, okay, actual weather predictions use complicated formulas and computers, and they aren't a matter of the weatherman going out and looking at the sky for a bit and going, oh, it's probably 30% chance of raining today. No, it's not that hodgepodge. But since we have guessing, and since we have intuitive estimations as a thing in everyday life, mathematicians decided to coin a term for it called subjective probability. So this is based on intuition. It often involves little or no mathematical data. And, well, calling it an educated guess may or may not be slightly glorifying it. This is based on relative certainty. So an estimation of events between 0 impossible to 1 certain. For example, if somebody tells you to estimate the chance that all classes will be canceled tomorrow, you should not say 0. You should say that it's very close to 0, because it seems unlikely that a sudden event will arise that cause all classes to be canceled tomorrow. Yeah. Guys, are we sure that tomorrow or overnight there won't be, say, a random meteor that falls on the school? That and various other possibilities could all result in all classes being canceled tomorrow, despite the weather forecast having no terrible weather and, well, no other potential causes that are immediately apparent today. So there are very few events that we can actually say are impossible based on subjective probability. We can look at a spinner that has, say, one section that's red and another section that's green that do not touch, so you can't say that a needle that lands right on the line is both, and say that the probability of getting both red and green is 0. Yeah, you can say that. That's subjective probability. But for everyday events, impossible is a strong word. Please be very careful when using it. So let's estimate some subjective probabilities. So let's say a random toilet in your school is found in a girl's or woman's bathroom. For the record, since the plumbing is roughly the same between males and females, The main difference in how long men take to go to the bathroom versus how long females take, well, there's a handling the stalls, but besides the stalls, there is also the fact that you can fit more urinals per length of wall or per volume of space than you can fit toilets. Having said that, if we're talking about toilets in a school, there are a lot more toilets in a girl's bathroom than a boy's bathroom. There are a lot more toilets in a woman's bathroom than a men's bathroom at a school. You can reasonably say that about 70% of the toilets in a school are found in a girl's or woman's bathroom. Or female's bathroom. Okay, better? Now, what about a random person in your school turning out to be a student? Say you just grab some random person blindly in your school, and they turn out to be a student. Well, hey, schools are generally pretty well known for being pretty full of students. Result? Well, it's probably actually rather greater than 90%. But wording of the problem can be pretty important. A random person found in your school or caught in your school would probably evoke a rather different subjective probability of them being a student than just a random person in your school. And then there's a random person sitting at a desk in your school. Well, most of the time, people sitting at desks in schools tend to be students. And then there's random person writing on a blackboard in your school. Yeah, different word choices or described rows can radically alter subjective probabilities, even though we know that many students do write on blackboards. How about we turn on the TV at some point, some random time, and what's the chance that there's an advertisement playing? Let's think about this. Well, for a half-hour TV show, you have advertisements at the beginning and end, and you have intermission in the middle. So something like 6 minutes or more of advertisements. 6 minutes out of 30 minutes is actually a 0.2, but it's pretty easy for many channels to have advertisements playing a little bit more than that. So saying 0.3 is not unreasonable, as long as you can rationalize your subjective probability in a way that your teachers can accept, and it's reasonably close to what others can come up with, well, then you're probably fine. Of course, if you say that you turn on the TV at some random time and an advertisement is playing is 0.9 because I can switch the channels until I find one where there's an advertisement. No. That's not funny. Even though it's true. This kind of presumes that we not be trying to troll our teachers, because remember, if you troll your teachers, they mark your stuff and they may decide to troll you back. Now that we're done with that public service advisory or announcement, in summary, the probability of an outcome is a measure of how likely it is to occur in a probability experiment. The experimental probability is based on experimental data. So we do things a whole bunch of times and we consider how many times a particular outcome showed up, dividing by the total. You can just write n, especially later, once your teacher is reasonably sure you know what n actually is. And that would be the probability, the experimental probability of that particular outcome. Favorable or unfavorable just means, did we get the outcome we happen to be looking for in a particular case? So probability of red is a favorable outcome. Probability of blue, blue is a favorable outcome. Probability of yellow, yellow is a favorable outcome. Subjective probability is an estimate of the likelihood of an outcome or event based mostly on intuition. Intuition, oh well, yeah, it's kind of a guess, but it usually relies on life experience, which makes it an educated guess. Well, that's it for this section. Next section, we get to talk about the difference between theory and reality, namely theoretical probability. So, see you later.